Now that we know several things about taking derivatives of functions, we now can start applying them a little bit. One of the big areas that I can use derivatives for is when I'm comparing how fast something is changing with respect to time. An example of that is, I don't know if you've been over near the drawbridge in Grand Haven, but right next to that drawbridge there's a big sand pile, and probably in Muskegon there is one too. But there's a big sand pile and sand and gravel and salt for the winter, and there's a kind of a conical shaped pile, and what is happening is as they're taking the salt trucks, they're taking sand off of the pile. They want to make sure that they don't take sand off too fast, because if they take the sand off too fast, it probably just would start making the pile crumble. So they want to make sure how fast the volume of that pile is changing is not too fast. So in that case, they would get to use a concept that's called related rates. At the end of this lesson, you'll be able to solve a basically related rates problem. All right, so this first lesson is just going to get you used to the concept of what a related rate is. A related rate is just rates of change of two or more related variables that are changing with respect to time. So how fast is something changing every second or every minute or something like that? Okay, for starters, we'll be given two functions that are both differentiable, so we can take the derivative and we'll find unknowns. All right, example 1. Let y equal x squared minus 3x. We would like to find dy dt when x equals 3, given that dx dt is equal to 2. So notice I've changed this up a little bit now. We're finding the derivative of y with respect to t, with respect to time, and we're also taking the derivative of x with respect to time. So we will be using the concept of implicit differentiation when we do these problems as well. Okay, so the first side, if we have y, the derivative of y is 1, but please remember that we're taking the derivative of y with respect to time this time. So we're going to put 1 dy dt instead of putting dy dx. Whoops, and I need to put a t there. Now equals, I'm going to rewrite that. That just looks awful. Dy dt equals, okay, the derivative of x squared is 2x, but this time I'm not taking the derivative of x with respect to x, I'm taking the derivative of x with respect to t, so I actually get to put something attached to the x as well this time. And then minus, the derivative of 3x is 3, but again, I'm taking the derivative of x with respect to time, so I actually do need to include that in my derivative as well. Okay, from here, it's just going to plug in what I know. I would like to find dy dt. I know that x is 3, so I'm going to get to put 3 in for my x, and I know that dx dt is equal to 2, so I'll get to put that in for all of those. So I'm going to have dy dt is equal to 2 times 3 times 2 minus 3 times 2. So let's see, that will give me 12 minus 6. So I know that y is changing at a rate of 6, whether it's like could be meters per second or something that's how fast y is changing with respect to time. All right, let's try another example. We're going to this time let xy equal 4. We would like to again find dy dt. We know that x is 8, and we are given that dx dt is equal to 10. So again, I know it's a related rates problem because we're changing things with respect to time. We want to know how fast are things changing. Okay, so for this one, again, it's an implicit problem, and it's also a product rule problem because those functions are being multiplied together. So we're going to have an f and a g. My f prime, the derivative of x will be 1, but again, we're taking the derivative of x with respect to time, so we do need to include the dx dt. G prime will be 1 dy dt, and now I'm ready to use the product rule. So f prime times g, 1 dx dt times y plus f g prime x times dy dt, and then equals the derivative of 4, since it's a constant, is 0. And now in this case, again, we have lots of information that we can plug in. They told us that x is 8. We know that dx dt equals 10. And notice, if I want to solve for dy dt, I've got this extra y happening in my problem. So how do I know what it is? It is time for a side trip. All right, so we're going to go off to the side and do a little extra step. We know they told us that xy was equal to 4. They also told us that x was equal to 8. So I'm going to have 8y equals 4. So I know that when x equals 8, y will equal 1/2. So that's my little side trip. Could not do the problem without it, but it was not within the same problem. So we've got y, and now I can put 1/2 in there. So now I have 10 times 1/2 plus 8 dy dt equals 0. So 10 times 1/2 is 5, plus 8 dy dt equals 0. Solving for dy dt, I'll have 8 dy dt equals -5. So dy dt is equal to -5/8. So that's how fast y is changing with respect to time. And you notice since I have a negative answer, I know that y is getting smaller with respect to time. All right, let's try one more example. We're going to let y equal the square root of 1 plus x squared, and we'd like to find dy dt when x equals 10, given that dx dt equals 2. So again, we're dealing with information that's changing with respect to time. So on the left side, the derivative of y would be 1, and we're taking it with respect to time, so we will include the dy dt. One thing that I need to do up here before I actually take the derivative of the right side, let's write it as a power. So this will be 1 plus x squared to the 1/2. And then I notice that I have parentheses, and if I have parentheses, I have the chain rule, which is I've got the wrapper going on and I've got the chocolate inside. So we are going to let the inside be represented by u. So if I were to rewrite that function, I have u to the 1/2. And so from here, remember when we take the derivative, we drop the 1/2 out front. Now I'll have u decrease my power by 1. That will give me -1/2, and then multiplied by the derivative of the inside. So the derivative of 1 plus 2x squared would be 2x, right? And I am now going to clean that up just a second though. Don't forget that when I took the derivative when I got 2x as my answer, I'm taking the derivative with respect to time. So I do have to include that on part of my answer. All right, cleaning this up a little bit, we've got dy dt equals 1/2 times 2x will just give me x, and I'll still have x dx dt. And then the u to the -1/2 is going to move down to the bottom and become the square root of u. But notice we need to still replace the u, so I'm going to have dy dt equals x dx dt over the square root of u, and u is 1 plus x squared. Okay, so that's my derivative, as long and awful as that was. Now we just get to plug in what we know. We know that x is equal to 10. We know that dx dt is equal to 2, and again down here we know that x is equal to 10. So if I figure this out, let's see, we're going to have 10 times 2, which is 20, and then over the square root of 10 squared is 100, plus 1 is 101. So that is how fast y is changing with respect to time. So hopefully now you can solve basic related rates problems.